Continuing on from the center of a distribution, next we can talk about the spread of a distribution. So we want to think about the center and spread as a pair that will always go together. So the spread or variation, those are interchangeable, refers to how much the data are spread out. A higher number for the spread indicates that the numerical values are more spread out. A lower number indicates the data are closer together. So just thinking about what we're getting at here, let's say we look at the first test in a class, and I say the class average is a 77. That's our mean. That's a measure of center, and so that's helpful. Well, the average is a C, but it doesn't tell you what most people made, because not every single person made a 77. Maybe there were some 77s in the class, but people scored below 77, above 77, and the average turned out to be that 77. So if I add a spread in there, it begins to help me see a range of values that are typical. And so there are two measures of spread that we'll look at in the class. And the first is the standard deviation. So when your data set is symmetric, the standard deviation is typically used to describe your spread, and it can be used from whether a particular value is close to or far from the mean. So mean and standard deviation are a pair that will always go together. The standard deviation is a measure of spread. It's a measure of variation. It's always zero or positive. It's never negative. And it can be calculated with this formula. It's the square root of the summation, this uppercase sigma summation. We're going to do x minus x bar squared, where x is each data piece and x bar is the mean that we just saw in the calculator. X bar is used to represent the mean. So each data piece minus the mean squared, add all those together and divide that by n minus 1, where n is the sample size. So if you had a sample of size 19, you would divide by 18. If you had a sample of size 8, you would divide by 7. Taking the square root of that will give you the standard deviation and shows how much your data typically varies. Key phrase, typically varies. So let's see the standard deviation in action. This video. So it's quite a long process. So let's go through it together. Suppose we keep track of how many minutes it takes for someone to check out at the grocery store, from the time he or she begins to put items on the conveyor belt to the time he or she exits the doors. The results of 10 randomly sampled customers are listed below. We want to find the standard deviation. So here, what we can do is we have our data pieces. The first person, it took them 10 minutes to check out at the grocery store. The next person took 12 minutes. The third person took 3 minutes. The fourth person took 9 minutes, all the way down to the 10th person taking 11 minutes. So the first thing I want to do is find each x minus the x bar, so each value minus the mean. So here what I want to do is first off find the mean. So we could use our calculator shortcut that we used in the last video. We could also do the old school way, just add these together, divide by 10. So if we do it that way, say 10 plus 12 plus 3, until we get all of our numbers in. And so the key here, if I'm doing this the old-fashioned way, adding these together, dividing by 10, I'm not going to put divided by 10 right now in my calculator, because that would just divide that number 11 by 10. I'm going to find the sum first. So add these together, it's 121. And then I'm going to divide that 121 by 10. So the average here, the mean, the x bar is 12.1. So now I'll take each x and subtract that 12.1. So I'll start with 10 minus 12.1. That is a negative 2.1. And it can be negative at this stage. If it's negative, it's below the mean. That's okay. And if it's positive, it's above the mean. That's okay as well. So here I would say 12 minus that 12.1. We get a negative 0.1. And then 3 minus 12.1 gives me a negative 9.1, and I'll keep going down the list and filling these in. So I'll get a negative 3.1 for the 9. If we do 14 minus 12.1, that's above the mean. That's going to give us a 2.9. Sorry, a 1.9. And then a 0.9, another 1.9, 0.9. 22 minus 12.1, that's 9.9. And then 11 minus 12.1 is a negative 1.1. Now, here's the thing. If I add all these together, if I say negative 2.1 plus negative 0.1 plus negative 9.1 plus negative 3.1 plus the 1.9, all the way down the list, what's going to happen each time this step, the total is going to be 0. These negative values here, started at the end, are going to cancel out with these 5 positive values. That's why we have the squared in our standard deviation form to keep these from canceling out. So I'll move to that negative 2.1 and I'll square. So I'll say negative 2.1 and then square that. Now notice on the carry I get a negative 4.41. That's not right. Negative 2.1 squared is a positive 4.41. You're squaring negative 2.1. You're saying negative 2.1 times another negative 2.1. A negative times a negative should be a positive. When I just say negative 2.1 squared, it's only squaring the 2.1 and not the negative. So I would have to say it's negative 2.1 in parentheses, this whole thing squared. There's the 4.41. Really, we know the negative times the negative is going to be a positive. So when I go to squared, I can just say it's 0.1 squared for the next one. Gives me a 0.01. And then I would move to my 9.1 squared, even though it's negative. I know a negative times a negative, once again, it's a positive. So 9.1 squared gives me 82.81. And I'll just continue filling in my table. So 3.1 squared is a 9.61, 0.80, 3.61, 9.9 squared is 98.01, and 1.21. And so now what I want to do is add these 10 squared values together. So the 4.41 plus 0.01 plus 82.81. Happen to have done this ahead of time. It is 204.9. So essentially, I've done the top part of my formula. I've taken each x and subtracted the x bar. That's what I did in the first column. Then I squared all of them. That's what I did in the second column. And then this sigma, this summation, it means add them all together. That's what we just did. It's 204.9. So my standard deviation is going to be the square root of 204.9 all over n minus 1. Well, n in this case, the sample is size 10. So n minus 1 is equal to 9. So it's 204.9 divided by 9. And you can do this multiple ways. I'll just type this in all at once. I'll hit second and x squared to grab my square root on my TI calculator. 204.9 divided by 9. And I'll close those parentheses. So it's all under the square root. And there's my standard deviation, 4.771. That's in minutes. So what I'm saying is the average amount of time it takes a person to check out is 12.1 minutes, about 12 minutes. But it doesn't take everyone exactly 12.1 minutes. Some people take shorter time. Other people take a longer time. And so what I'm saying is it varies typically by about 4.7 or by about 5 minutes. So what we could do is we could say 12.1 minus, let's say that's 4.8, and then 12.1 plus 4.8. And that tells me where most people are in their checkout times.